Okay, today we want to talk about the von Mises yield criterion, which you might have anticipated even before the class started this semester, because it's probably something you've been exposed to in some of your previous engineering courses. So we're going to talk a little bit about how it comes about, why it takes the form that it does. But before we begin, I want to remind you with a couple highlights from our previous lecture. So I'll just say that previously we showed the following. So previously we showed, and this is all related to the octahedral plane, that number one, the octahedral shear stress, okay, which we're going to call tau naught, octahedral shear stress, okay, octahedral shear stress that we'll call tau naught, was independent of the hydrostatic stress. Okay, number two. The octahedral normal stress was independent of the deviatoric stress, and in fact it depended only it depends only on the hydrostatic stress. Okay? And we were able to show that in fact the octahedral shear stress was related to the deviatoric invariant J2 by the following: tau naught squared is equal to 2/3 J2. Okay? Why do we care about that? Because tau naught is proportional to an invariant, to a deviatoric invariant. Okay? Okay, we didn't prove this, but I'll also just say that additionally, okay, it can be shown that the octahedral shear stress tau naught is actually the average shear stress over all planes. So tau naught is the average shear stress over all planes. Okay? So based on really the assumptions, these features, it probably makes sense that we might want to create a yield theory on the basis of this. So let's see if we can state that. So if we want a yield function that's independent of hydrostatic stresses, okay, independent of hydrostatic stresses, and why did we want that? Well, that was sort of per our mechanistic rationale, right? Right, namely that dislocations move only in response to a shear, or at least they glide only in response to a shear, and chain sliding is likely to happen during shear motion. So we want to eliminate the hydrostatic component from my criteria and focus only on the deviatoric component. Okay? So maybe we could propose a yield function. And if we did, it would probably be only a function of J2. That is only a function of J2, right? So we would write that f, the yield function, is some function of J2. And if we were just looking at something related to the octahedral stress, it might look like, possibly something like this, let's say. So possibly, how about f is equal to this quantity tau naught squared minus K naught squared, which we could also write as 2/3 J2 minus K naught squared, where this is just some material constant. Okay? That might be something that you would try. You'd say, well, I think yielding is going to happen when, in this case, the octahedral shear stress, which I just told you is the average shear stress over all the planes, but we also know it's dependent only on the deviatoric component and ignores the hydrostatic. Right? If it reaches some critical value, maybe we would want to call that yielding. Okay, so that's one way to think about how we might want to construct a yield function. Okay, how about some other considerations? Well, so let's go ahead and consider this problem from an energy perspective. So consider from an energy perspective. So we haven't talked a lot about energy, but let's just go ahead and consider the strain energy density in the material. So consider the strain energy density, which we'll call U. Okay, U in an elastic material. Okay. Okay, so what are we trying to go with? Well, what we want to ultimately say is something like maybe there's a critical amount of strain energy that we can accommodate, at least in the deviatoric side, before yielding happens. So this would be another type of consideration. So let's just go ahead and write that. We would have that U is going to be equal to our classic strain energy density for an elastic material, which is just 1/2 sigma ij epsilon ij. And of course we need to talk about the deviatoric side. That was our goal. So let's break this into deviatoric and hydrostatic components. So the stress broken into deviatoric gives us Sij, that's the deviatoric stress, and then plus the hydrostatic or spherical stress, which is just 1/3 sigma kk delta ij. And then the other is very similar. I'm just going to write this as epsilon ij prime, which is the deviatoric strain, then plus 1/3 times epsilon ll delta ij. Okay? And then we just go ahead and carry out the multiplication. The 1/2 still pulls out, and with inside we're left with Sij epsilon ij prime. And then now inside here I have this plus 1/3 sigma kk delta ij times epsilon ij prime gives me epsilon ii prime. And then plus, I'm going to now multiply the outside, 1/3 Sij, let me back up, 1/3 times epsilon ll delta ij times Sij gives me Sii. And then I have, in this last term, I have 1/9 times sigma kk epsilon ll times delta ij is delta ii, which is just 3. So I can go ahead and maybe erase this and write this instead of 1/9, this just becomes 1/3. Right? Okay. Well, we know what the trace of a deviatoric tensor is. It's 0 identically. So this term goes to 0. This is our deviatoric stress, so that term goes to 0. Right? And we're left with 1/2 Sij epsilon ij prime plus 1/6 sigma kk epsilon ll. So what we see is that the strain energy density is actually also decomposed into deviatoric and hydrostatic components. So this is actually the deviatoric component of the strain energy density. We'll call that U prime. And then this is obviously the hydrostatic component. Okay. So let's go ahead and take a look at this term here. What does this deviatoric strain energy density look like? So let's say consider U prime. And I want to also note that we can use a Hooke's law here. So we use Hooke's law to write, right? We have an equation for the deviatoric elastic strain, epsilon ij prime, right? That's just equal to 1 over 2 mu times Sij. Okay? So, if I substitute into this equation here for U prime, I end up with that U prime is equal to 1 over 4 mu times Sij Sij. Okay, but now let me look at this term right here. If you see, I don't expect you to have memorized it, but I'll just try to jog your memory here. If you look at that term, what I hope you remember is that that actually is by definition 2 times J2. So that U prime is actually equal to 1 over 2 mu times J2. So if we want to interpret yielding as some critical deviatoric strain energy density when it reaches a critical value, so let's just write that. So if we interpret yielding, so interpret yielding as when a critical deviatoric strain energy density is reached. Okay. So if we interpret it in that fashion, then we would still write that f must be a function of only J2, right? But maybe we would choose, so I'll say this is a possible, right? We might choose something that says f is equal to 1 over 2 mu times J2 minus some whatever material constant. It doesn't have to be the same K naught as we had before. Okay? So that would be an equivalent statement. What the von Mises criterion is, it could actually be interpreted in both ways. So what the von Mises criterion tells us, or begins with, it says, look, I just think that there's multiple reasons here to define a failure criterion or a yield function just in terms of J2, the deviatoric, the second deviatoric invariant. And so, let's just say that we can do it very generally. So, the von Mises criterion, or how about yield function, since that's sort of the way we talk about it now in this plasticity class, is just a generalization of these observations. Okay? So it's a generalization of these observations. And it's a little bit simplified, right? It doesn't have the coefficients in front of it. It says, yeah, I want f to be a function of J2. If I want that, then let's just make it simple and say that f is equal to J2 minus some K naught squared, right? This is the von Mises yield criterion, okay? So this is the von Mises, how about yield function? Okay? Okay. So what does that give us? Well, remember at the very beginning we said that this function, all this is basically a scalar multiple of, let's say, the function that we had proposed initially just based on the octahedral shear stress. And so what that said was that basically we would look at the radius in the octahedral plane, and that anything normal to that would be a hydrostatic stress that wouldn't contribute any additional amount to failure. So what that actually gives us is a surface in 3D stress space that looks like a circular cylinder with its axis that is orthogonal to the octahedral plane, or it's in the 111 direction. Okay, so let me just say this for you. We can visualize, okay, the von Mises surface or yield surface. Okay, we can visualize the von Mises yield surface as a circular cylinder. Okay, with its axis orthogonal to the octahedral plane. To the octahedral plane. Okay, so that means that it's in the direction of nu hat that we talked about before. In the direction nu hat, which is equal to 1 over root 3 times 111. Okay? So let me see if I can show you what that looks like. Okay, so here's what we're looking at, and what we want to say on here is, so there's your cylinder. This direction, if I can draw a right angle here with this plane, okay? This direction, that right there is nu hat, and that's equal to what we said up there. So 1 over square root of 3 times 111. Okay, and you can see that this basically goes off into infinity. This is what in this particular plot they're calling the hydrostatic axis. Okay. The other feature that's important is this blue plane that's highlighted, and it actually goes through the origin. So it's basically a cross section of this cylinder at the origin, and that's called the pi plane, or sometimes it's called the deviatoric plane. Okay. And then obviously there's some radius that sits here. This would be r, right? That radius, it holds fixed the whole way up and down the cylinder. Okay, so a couple things we could do. We could look down this axis nu hat and look straight onto the yield surface. So if we do that, you'll see we looks like a circle. Okay, so if we look down nu hat, the axis, okay, onto the pi plane, the surface appears as a circle. Okay. So let's try to draw that. It's going to be basically looking right down here. It gives us straight up thirds. It's supposed to be in nice thirds. Not perfect. And then this out of the plane, this quantity, this is I'll draw a circle to show that it's out of the plane. So this is coming straight at us. That's nu hat. And then this gives us just a pure circle as we look around it. So, right, this is the boundary f equals 0, right? And that's this here. Let me draw up there. That boundary is the f equals 0 boundary. Okay? And then there's obviously, we have our, if we want, we have some radius that we can talk about that is r. Okay? What you're probably used to when you look at the von Mises failure envelope is something that looks like an ellipse. And it turns out if we take a slice, so imagine, let's say in this 1-2 plane, we took a slice of this. This circular cylinder, when we cut it along the 1-2 plane, will give us an ellipse, and that's exactly what we get. So we can say that looking at a slice in a more traditional, in a 2D stress space, which is what you're probably used to, at least from your machine design or something like that, it appears as an ellipse. Okay. So let's just take the 1, 2. So this would be the sigma 2, 2 direction, and this would be the sigma 1 direction. So let's see here. Let's go over 1, 2, 3, 4, 5. Plot that. I should have this. 1, 2, 3, 4, 5. Plot that, and then we come over here like this. Do the same thing on the negative side. So 1, 2, 3, 4, 5, and then down here, let's see, 1, 2, 3, 4, 5, something like this. Okay, and we end up with an ellipse that looks like this. That would be okay. And this is, again, the f equals 0 plane. So it hopefully looks a little more familiar to you. Okay? In general, whenever we have a yield function, or we would call them sometimes plasticity theories, that depend only on J2, we call that J2 plasticity. And as you encounter plasticity literature, you're going to see this sort of come up quite frequently. Okay, so I'll just note that. The yield function let's say of this type give rise to what's called J2 plasticity. Okay, and now you know hopefully what it means. Right? It means you're going to have plasticity that's driven entirely by the second invariant of the deviatoric stress tensor. And hopefully after this lecture, you know why. It's because both from the perspective of an average yield stress, which is going to be an average shear stress, which is the octahedral shear stress, and also that being independent of the hydrostatic component, or from the perspective of the deviatoric strain energy, either one of those would lead you to a J2 type plasticity theory. Okay? The only thing that's remaining is how do we define that K naught value? So typically we're going to get that from experiment, or we're going to look it up somewhere. But I'll give you just some quick relations. So the value of the constant K naught. And one thing I'll mention too about this is that obviously K naught, we're talking about initial yield surfaces, right? So this is just the initial. What happens after that depends on how we've decided to harden the material. But so that's why this value potentially could change depending on the hardening. But so the value of some constant K naught can be related to the following. So it can be related to, number one, we could relate it to the yield stress and uniaxial tension that we would measure. And if we did that, we would say that K naught is equal to y over root 3, where y is equal to the yield stress in uniaxial tension, right? So you could easily read that off a stress strain curve. And then you could also relate it to the octahedral shear stress, right? Which we've already kind of done. We could say K naught is equal to then the square root of 3/2 times tau naught, where tau naught is the octahedral shear stress. Okay. So hopefully that all made sense. Hopefully you understand why the von Mises criterion that you've presumably been exposed to in your previous undergraduate career, how that comes about, why it comes about, and I guess why it's been so useful and kind of is the default when we talk about plasticity theories.